Okay, we're going to look at equilibrium. This is a topic you did cover at GCSE. It's quite one of the harder topics to discover to cover when you're in year 11, and we're going to have a more in-depth look into it now. But the first bit will be covering GCSE stuff. Okay, so here is an equilibrium reaction. It's between nitrogen and hydrogen to form ammonia, and that's, of course, you may remember the Haber process. So this, so if we start, we've got the graph here. This is the percentage converted to ammonia of the nitrogen and hydrogen. So at the point there, we're going to have 0% ammonia, 0% converted, and it's all nitrogen and hydrogen. As time goes on, the amount of ammonia goes up. Now you would expect this probably to carry on going until it all being converted into ammonia. But as you can see, that doesn't happen. It appears to sort of get stuck. I would say the reaction seems to stop about there, at about that time. And we say that equilibrium has been reached there. So EQM, on the right side of equilibrium all the time. So what's happened? Well, it looks like the nitrogen and hydrogen have stopped reacting. They haven't stopped reacting. They're still reacting all the time. But what's also happening is the ammonia is turning back into the nitrogen and hydrogen at the same rate as it's being formed. And so it looks as though nothing has happened. Okay, and that leads us nicely to the two characteristics of an equilibrium, of a reactant at equilibrium. And they quite often ask this, 2 marks. Okay, and the first one is the concentration, right, the conc of reactants and products do not change. And secondly, which explains the first point, the rate of the forward reaction is equal to the rate of the backward reaction. Okay, so that's what's going on at equilibrium. Okay, now just a little bit of jargon here, which is called the position of equilibrium. Right, that means how much product have you got relation to reactants. So you've got lots of products, like lots of ammonia in this case. You'd say the equilibrium position lies to the right. Right, okay, whereas if you had lots of nitrogen and hydrogen, you'd say the position lies to the left. So that's that little bit of jargon just about right and left, which we'll come across, we'll be talking about quite a lot. Let's just see what happens. If you change things like the temperature, it will usually change the position of equilibrium. And in this reaction, so if you do it at a higher temperature, what happens is you get a line something like that. Okay, so here it's steeper because the temperature is higher, so the rate of reaction is faster. We're not really so interested in that here, though. We're interested in the fact that this line levels out at a lower level of ammonia. So this is at higher temperature, this one here. So just so you understand this sort of way of describing things, so you'd say at a higher temperature, the equilibrium moves to the left. In other words, it moves in favor of in favor of the nitrogen and the hydrogen. Okay, so that's what we mean by position of equilibrium. Okay, so now, before we come to this next reaction here, I just want to talk about that thing there, Le Chatelier's principle. Okay, and what he said was, whatever change is imposed on a reaction at equilibrium, the position of equilibrium moves so as to oppose the change. So that means if you try and make it hot, the reaction hot, it will try and make it cold. Okay, how can it do that? By moving in endothermic direction. If you try and increase the pressure, it will try and make the pressure drop somehow. We'll talk about that later. If you add more reactants, it will try and use up the reactants, and so it will go forwards and make more product. Right, now just to illustrate this, is just a nice little experiment which you may have done in class, okay? And it's using this this reaction here, which is nitrogen dioxide, okay, this one here. Right, what we've got is we've got NO2, okay, and it dimerizes, so I need to balance that, put a 2 in front of that. It dimerizes to form N2O4 there. Unfortunately for us, the NO2 is a reddy brown color, whereas the N2O4 is not quite colorless, but it's all, for all intents and purposes, we can consider it to be colorless. So that's quite convenient for us, because if you've got if you've got a little glass tube and it's sealed at both ends, and in there you've got a mixture of NO2 and N2O4. Now you can, if the equilibrium changes position, then the red color, the depth of the red color will change. So if it moves to the left in favor of NO2, it's going to go darker brown. If it moves to the right, the brown color will go paler. So it's quite a nice visual way of, without having to measure anything, you can just tell by looking which way the equilibrium is going. Now, with this one, right, so if we get 2 beakers of water and we'll get 2 of those tubes the same, and I've got one with hot water here. There is my tube, and that goes a nice dark red, so that means you've got a lot of NO2. The equilibrium is fairly over to the left, and this is hot water. Okay, do some little lines there, so this, the water's just come out of the kettle. Okay, and then this one, we put it in some cold water, maybe some ice cubes in it, and that reddy color fades a lot. It goes much paler. It's a much paler red color. Okay, so we can tell from that, and then just to show you that it is, the change is reversible. If you swap those tubes round, the colors will change the other way. So what we've established there is that when you make it cold, you get more N2O4, the colorless one, i.e., would say that the equilibrium moves to the right. And likewise, if you increase the temperature, the equilibrium here will move to the left. So let us just have a think about what Le Chatelier tells us about this. Okay, so he says, whatever we did to it, it will try and undo it. So let's say when we put it in the cold, what will the tube do? What will the reaction do? It will try to warm up. Now, the only way the reaction can warm up, it doesn't warm, but it tries to warm up, is it will move in the exothermic direction. So that tells us that this forward direction here is exothermic. And of course, it must follow from that the backward direction is endothermic. So that's a nice little demonstration of how temperature affects the position of equilibrium, and we can explain it in predicted the change in terms of Le Chatelier's principle. If the forward reaction is exothermic, you put it in cold water, it will move in the exothermic direction, so it will become more colorless. Right, so have a good look at Le Chatelier's principle there. Make sure you sort of got it firmly in your mind what it is. And in the next video, we'll look at the effect on position of equilibrium of changing the pressure.